Are you ready?
Listo, en tiempo. Muy buenos días a todos. Muchas gracias por estar aquí en este tercer día de la Escuela de Materiales. Y brevemente voy a presentarles la agenda para el día de hoy. En unos momentos será oportunidad para el doctor Dickey de la segunda sesión del curso sobre metales líquidos de 9 a 10:30. De 11 a 12:30 estará la doctora Sandra Rodil presentándonos también la segunda sesión sobre evaluación fotocatalítica de semiconductores. Tendremos un breve receso y posteriormente tendremos dos pláticas cortas dentro de las conferencias de vinculación de academia e industria. La primera será impartida por el doctor Saúl Piedra de 1 a 1:30 y nos hablará un poco de la vinculación académica o las experiencias que han tenido en el CIDES y CENTA. Y posteriormente la maestra Nicté Luna, que nos hablará de la importancia de la ciencia, que justo ayer trataban algunos de los participantes. Tendremos la sesión para comida y posteriormente regresaremos a la segunda sesión del curso del doctor Mauricio Torres. Bueno, sin más preámbulo, le doy la palabra al doctor Michael Dickey para que comience su segunda sesión. Good morning, Michael.
Good morning.
So you are perfect. You have the opportunity.
Is it okay to start?
Yes, yes, please.
Okay. Well, buenos dias. Good morning, everybody. Thank you for coming back. I'm really happy to see all your faces this morning. It's a nice way to start the day. So today I'm going to tell you a little bit more about liquid metals. It's actually on Friday I'm going to kind of switch subjects. So it's the last time we'll talk about liquid metals, at least for these talks. And for those of you that may have missed Monday, I just want to remind you that I'm a professor at NC State University, North Carolina State. We are of course, in North Carolina on the East Coast of the United States. And we live in Raleigh, North Carolina, which is considered a very nice place to live. And for those of you that are undergraduates, I hope that you'll come back on Friday because I'm going to talk a little bit about opportunities for graduate school. So this is just a reminder of kind of my plan for the week. So on Monday, we talked about liquid metal, talked about the fact that it's both a liquid and a metal. It's made out of gallium, got this oxide layer that gives it very unique properties. Today, I'm going to sort of switch gears a little bit, but still talk about liquid metal, but mainly be talking about particles and the interfacial behavior of the metal. And then on Friday, switch gears and we'll talk about actually polymers. So I think you'll really enjoy that too. So as a reminder, kind of one of the key ideas that I presented on Monday is that these liquid metals react with air and form a very thin oxide layer. And that oxide layer allows the metal to take on shapes that would not normally be possible with liquids. So I'm going to play this one more time so you can see that initially that this is the metal is spread on the glass side, sort of like paint. But then if you take this Q-tip, which has a little bit of acid on it, that acid removes that oxide layer and the metal will bead up. So what do we know about this oxide layer? Well, it's a few nanometers thick. And one way we know that is simply looking at it. So this is a transmission electron micrograph, TEM, which shows the thickness to be a few nanometers. And it forms spontaneously in air onto the liquid metal. Now, the second thing is it's passivating, and that's important because that means it forms, but it does not get thicker. And this is the reason aluminum does the same thing, and that's the reason you don't find rust on aluminum foil. It just forms a thin layer and it stops. And then you might remember that the liquid metal has indium in it to help lower the melting point, but the surface layer is just gallium oxide. So in the absence of this oxide layer, the metal has a very, very large surface tension. In fact, the largest surface tension of any liquid known to man. And so to kind of illustrate this is actually in base, 1 molar sodium hydroxide, which removes the oxide layer. And when you shake this vial, I'll play it maybe one more time. Let's see. When you shake this vial, there's enough energy to break the metal into little droplets, but it very quickly goes back together because one droplet minimizes the surface area and therefore minimizes the surface energy. However, if you do this experiment in conditions where the oxide can form, then if there's no oxide, two particles merge together and form a bigger particle. But if you have the oxide layer, that can help stabilize it. And so we and other people have used this to make very small particles. So for example, one way to do it is by what's called sonication. Basically, this is just vibrations, like shaking. And we can take the liquid metal and form particles. And this is what the solution looks like. It kind of looks like milk a little bit, but it's gray. And if you look at it with a fancy microscope, you can see the particles are very small, about 100 nanometers or so. Another way to do it is just by stirring, very aggressive stirring. This is called a high shear mixer, which just stirs very fast. And then another way to do it is by using microfluidics. And so we've done some work here where we've pumping the liquid metal. So the liquid metal is black. And we also pump another fluid, which you can't see because it's clear. And when we pump it, as it goes through this very small orifice, it causes the metal to break up into droplets. And this is actually taken with a high-speed camera, so it's actually going really fast, like really, really fast. And we can make perfectly monodispersed liquid metal droplets, as shown in this picture. Okay, so what is this good for? I'll show you a couple of examples. So I mentioned that one way to do this is by sonication. So again, you take some solvent and a droplet of the liquid metal, you sonicate it, which is just vibrations, and it forms particles. And this is what they look like. If you do an elemental analysis, you can see that there's indium in these particles, there's gallium in the particles, and then if you look at the oxygen, you can actually see the oxygen, the oxide that forms on the perimeter of this droplet on the outside. Okay, so we've taken these. This is a picture of an actual vial of ethanol with the liquid metal, and we sonicate it, and we get the very small particles. Again, this is what they look like. And the idea that we had initially was, well, what if we cast a film of these? Then we could actually make a conductor out of this. But the problem is actually it's not a very good conductor because the electrons have to jump from here to here to here to here, just jump, 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 jump. And it's not a good conductor at all. However, because the liquid metal it's liquid, you can push on it and the particles will merge together. So that's exactly what we did. We took a silicone and we cast a film of it. And we then, well, you'll see in this video, you can stick electronic components into this. So this is just a simple LED and some copper wires. And you'll see that even though there's liquid metal there, it's not conductive. It's very resistive. But if you use a pin to apply some pressure, that will break the little particles. And so now it's conductive. And so you can actually draw this sort of circuit board by hand. Okay, so that's one example of things that you can do with the particles. I'm also going to show you that you can use them for reactions that are useful. And this first one we actually discovered on accident. So this is I think a good lesson for students is that sometimes it's really good just to try things because sometimes you don't really know what's going to happen. It's hard to guess. So the first thing in terms of reactivities is polymerization. So again, this was an accident. It was a really fortuitous accident. So here's a vial with a droplet of liquid metal. Remember, this is E is eutectic gallium indium. And it's sitting in a solution of monomer. So monomer are molecules that can react together to form a polymer. So any sort of polymer that you have started out as a monomer. Well, Usually, to get polymers to form, you have to use heat or light, and you have to use a special molecule called an initiator that will cause the polymerization to proceed. Here, we don't have any of those things. There's no light, there's no heat, um, there's no initiator, and we simply sonicate it. And when we're done, we flip it over, and you can see it's turned into a gel. So this is really exciting because it suggests that you could use mechanical energy, just vibrations, to cause chemical reactions. So I just want to remind you that gallium is not the only metal that forms an oxide layer. Many, many metals do, and aluminum is a great example. Now, aluminum is actually a very dangerous material because it's quite reactive if you use metal powder, excuse me. But it's because of the oxide layer, that it doesn't react. So, aluminum powder can be used in like fireworks and other things, and it can burn very, very aggressively. So the idea here is that, certain metals, which are very reactive, actually don't react because of the oxide. In our case, because of if you focus right here, this is again, the oxide layer with the liquid metal, and these red things are the monomers, the molecules. And what we think is that when we sonicate it, we break the oxide and we expose this very reactive metal to these monomers, and we start to form polymer, which again are these long chains. To be honest, we don't completely understand this mechanism, and it's something we're still trying to figure out, but I'll give you some of the things that we do know. So first of all, we did this same experiment in the presence of this molecule here, this black molecule. And this black molecule is known to be a free radical inhibitor. So you may have heard of free radicals, particularly with regard to human health. You don't want to have radicals in your body because radicals are very reactive. And we think that we're creating radicals in this example. Well, this black molecule can actually prevent those radicals from causing polymerization. And when it's working, it will turn orange. And so you can see in this vial, in the presence of this molecule, first of all, it's not a gel. You can see it's a liquid-like. So if you tilt it, you can see the liquid. And then secondly, it turns orange, which means that it's forming radicals. You can also measure radicals using this a special technique called electron paramagnetic resonance. It's called EPR. And I'm not an expert in it, but basically when you see peaks in this measurement, it tells you that there's radicals. So we've measured radicals kind of indirectly and directly. And then finally, we use this technique that's called time-of-flight SIMS, and I don't want to go into the details, but basically it allows you to identify chemical species that form. And we were really excited because we saw gallium directly connected to the monomer. So if I go back, we see that these chemical species are directly attached to the gallium. And so that suggests that the metal itself is initiating the polymerization. So perhaps the best way to convince yourself is to actually look at the particles. And so this is a liquid metal nanoparticle, and you can see it here. It's sitting on a piece of graphite, which is what this other stuff is here. And it's kind of boring. It's just a sphere. Now, if we do this with the monomer, which is called acrylamide, this is a material that's used in contact lenses, you'll see that there's this polymer that is on the surface of the particle. So again, we don't completely understand it, but we do think that the gallium itself is causing the polymerization to initiate. So we ultimately use this to make a really stretchy material. So this is polyacrylamide, which is, again, it's kind of a very common hydrogel. And here it is. We grab it and you can pull it to about 15 times its original length. So we can use this to actually make polymer. Okay, so that's one example of where gallium reactivity could be useful. Another one is actually sort of good and bad. Gallium behaves a little bit differently in water. And so, what I've shown you up till now is basically sonication in something like ethanol or other liquids, and we just form particles, and they look nice, but they're kind of boring. Well, we tried to do this in water, and it was very surprising because instead of getting spheres, we got rods. And it's a liquid, so we kind of thought, it should form spheres. So we did some experiments. We weren't sure if these were because of sonication or some other effect. So what we did is we took the bulk liquid metal, sonicated it, but did it at low temperatures to make sure, because sonication can kind of make the solution hot. So we sonicated it in an ice bath, and we actually got spheres. We then took those spheres and we heat them up at 70 degrees for 10 minutes. And we find that we actually form gallium oxide monohydroxide, so GaOOH. And that is a solid, and it's a crystal. And this is what it looks like. It's a rod. But, because these particles have gallium and indium, we also see some indium particles left behind. So if you do an analysis of this, you'll see that the rods are gallium or gallium oxide, and the particles are indium. And so we're actually able to separate the gallium from the indium by simply reacting the gallium and not the indium. So this is kind of interesting, because what this means is that you can take a particle that is a sphere, by heating it, you can turn it into a rod. So this is what the rod looks like if you just focus on it, and you can see it's crystalline. So it's not a liquid, it's a solid rod. All right, so it turns out that this is potentially useful, and I'll show you a couple of examples. First of all, instead of using heat, we can use light to trigger this. And so this was a collaboration with Professor Gu's group, and he had this idea. So this was really his idea, not mine, that you could take cells, and so imagine these could be cancer cells that you want to kill, and you take the particles, and the particles, which are shown here, will go into the cell by a process that's called endocytosis. This is basically the particles get consumed into the cell, into what's called an endosome. So now they're inside the cell, and then if you expose them to light, you can convert them from spheres into rods. And if a rod takes up more space, it's going to push outwards, and it's going to actually break apart the cell and cause it to kill the cancer cell. So this was pretty exciting. I think a nice application of gallium particles. Now, it turns out that you can actually kill bacteria as well, and I'm going to show you on the next slide. So I'm going to spend a little bit of time talking about how to move the particles around in a way that I think is useful, or at least interesting. So in the first way, we use magnets. And what we do is we take the liquid metal with some iron powder. So these particles have a little bit of iron inside of them to make them respond to magnets. This was done by my friends in Australia. And so I contributed only in a very small way. So this is the names you see here are the people who led this work. So anyway, if you apply a magnetic field, this was kind of interesting. These particles actually become rods, and they somehow kind of spin around. So one possible application of this is is to kill bacteria. So biofilms are these layers of bacteria, and sometimes if you get a wound on your skin, these biofilms can form, and in some cases, they don't go away. They can actually be deadly. And so there's a lot of interest in trying to figure out how to get rid of these. Now, one way is to use antibiotics, of course, but some antibiotics are not working very well anymore because the bacteria grow resistance to them. Another way to do it is for the doctor to come in and just cut it out, which sounds painful. And of course, that doesn't remove all the bacteria. And so basically, is there some other way to do this in a way that's not, antibiotic resistant? So what we do is these green things are the bacteria. These are if I go back, these are the gross looking things that are on the skin, and they form a film. And that film, like I said, it's like a barrier. It prevents oxygen and nutrients from getting into your wound to keep it from healing. So we put these particles, and then we apply a rotating magnetic field. So the magnet just spins, and those particles start to become spiky. They become rods. And we think that we don't, again, this is another thing we don't really understand. It just happens to work really well. These will kill the bacteria, which now they show up as red, and eventually all the bacteria goes away. So as an example, these funny names are two different types of bacteria that are very common. So if you grow them in a petri dish, this is looking top down, you'll see that they look purple, and because they're stained purple, I believe. And if you use a small magnet, you can see that the bacteria in the middle of this dish gets killed. And if you use a larger magnet, it kills a bigger area. So basically, wherever we treat it with these gallium particles, it seems to be killing the bacteria. So I think it's a physical mechanism, but there's also, it's known that gallium, well, Ga3 plus is known to have antibacterial properties. So there could be multiple things that are happening here. Okay, so magnets are one way you can move particles, but only if they have magnetic materials inside of them. So for example, iron. Another way to move these things is to use electric fields. And this is some recent work, and I'm really excited about it. So there's this effect called dielectrophoresis, which is basically using electric fields to move particles. So this was done with some amazing undergraduate students. These two ladies here came and visited my lab from Singapore about a year ago, and this is their advisor in Singapore, Professor Matthews, and this is their other mentor, Ankit. So they were amazing students, and they came and tried out this experiment. Well, basically what we did is we made liquid metal particles, and you can see them here. They're these spheres, and they're sitting in silicone. So it's a liquid. It's an oil, like an oil-like material. And as you can see, there's not enough particles here to form a conductive path. So this is a perfect insulator. However, if you apply an electric field between these two gold electrodes, if you watch carefully, you'll see that the particles merge together. And so this is again called dielectrophoresis. Maybe I'll play it one more time because it happens quite quickly. If you watch the bottom of this video, you see that the particles merge together, and because they're liquid, they will actually center. They'll stick together and form a conductive path. And so the beauty of this is, in previous literature, usually you have to add many particles to make a good conductor. And in our case, we only have to add a few because we can assemble them using electric fields. Okay, so as one example of kind of just a neat demonstration, this is a circuit that has obviously two copper electrodes, and in the middle there's a gap, so it looks like this. And you'll see that the students are going to come in and they're going to cut it, and they're actually going to completely remove that material. So they're going to pull it away with tweezers. So now there's no connection in this circuit. However, if you take this ink, which has the particles in it, it's still not conductive. But if you apply an electric field, you'll see that you can assemble the particles and restore the connection. Now the silicone, the beauty of this is we're doing this in silicone, so you can then heat it and the whole thing becomes a piece of rubber. So you could have a stretchable conductor that if it gets broken, you can add this ink, assemble it, and have it heal. Okay, so I've shown you now two ways to move the metal, and magnets and electric fields. Now another way to do this is actually using what's called wetting gradients, which is kind of a term I kind of made up, although other people have used it too. And just for fun, I will show you, this work is really just for fun. As far as I know, there's no application. But I hope that you know who this person is. This is Usain Bolt, who is, I think, still the fastest man in the world. He's just an incredible athlete and can run, beat the best athletes in the world at the 100-yard dash, by quite a distance. So the question is, can we make liquid metal run faster than this person? So I'll leave you in a little bit of suspense, but I will answer this question. So the key idea to make this work is that gallium likes other metals. So if you take gallium, gallium indium, so the drop of gallium indium, and this is a silver film that is glued to the surface. So it's just resting on a surface, but it's glued down. And this is done in acid. So if you hit play, you can see that the liquid metal will wet the silver. Now, if you take that same piece of silver and you have it floating in solution like a noodle, and that's what you're seeing here. Now, if you take a little piece of wood and touch the liquid metal, okay, so here's the liquid metal, here's the little piece of silver, and if you touch it, the gallium wets the silver and it actually pulls it into the gallium. It sort of eats it. And it's because the gallium likes to wet the silver. And so it's trying to maximize the amount of contact area it has with the silver. It probably dissolves some of the silver and eventually it becomes saturated. All right, so there's two extremes here. On the left, the silver is glued to the surface. Over here, the silver is floating. So then we thought, well, what if we put a film that's just loosely adhered? So imagine this is your film, and you just loosely adhere it to the surface. So there's a little bit of force, but not much. So we did that, and you'll see that the liquid metal moves along that film. And so all that's happening is we're just putting a droplet of liquid metal in the presence of acid so that there's no oxide, and it just zips along this film. So here we do it in acid. You can also do this using electrochemistry. So if you look over here on the left, you'll see that there's a droplet of liquid metal. Here's an electrode, and as soon as we apply a voltage, we can remove the oxide and it will zip right along. And it's very fast. So we can do this on curved paths to get it to follow different paths. It will go around a circle. And we can even make it go uphill. So this has to be taken with a high-speed camera to see this. So you'll see this is a hill. And if you look carefully, it's actually pulling the film off of the surface. So let me play that one more time, because this was actually a really important experiment for us. If you watch, is it gonna work? There it goes. If you watch it, the leading edge of that droplet is sort of pulling that film off the surface. And so what we think is happening is, if you imagine that this is the liquid metal and this black thing is the silver film that's resting on this surface. So it's resting here and then it gets pulled up. Well, ends up being a force that's pulling it along. And the best explanation, sort of analogy I can think of, is imagine the forces. So these guys are pulling a film off of a surface. They have to pull up, but they also have to pull over. So there's a force in two different directions. Well, it turns out that it's a little bit more complicated. And so my student, who was really good, he noticed something interesting. So if you look from the top down at these films, what we think is happening is there's an electron. The gallium wants to oxidize, right? Well, the gallium, so therefore it wants to give up an electron. And the question is, well, where does it go? Well, it can reduce protons in the solution. So you can actually get protons from the acid that will form hydrogen bubbles. And so if you look top down, you'll notice, this is again a high-speed camera, you'll notice as the liquid metal comes along, that film sort of wrinkles before the metal gets there. And so I'll just let it play one more time. So you can see even over here, the film is wrinkling. So then we looked from the bottom, and again, as the liquid metal comes along, you can start to see bubbles form. And amazingly, these bubbles are forming between the metal film and the substrate. So that means these electrochemical reactions are occurring between the metal and the substrate, that's shown here. And I think that helps to lift the film off of the surface. Okay, so I asked you if this is faster than Usain Bolt. Well, we're going to cheat a little bit, and we're going to report our speed in terms of body lengths per time, because so if you look on this axis, body length per time, and that's really only fair because Usain Bolt, his legs are very, very long, and our little droplet is only about this big. And so if you do it this way, you'll see Usain Bolt is actually not very fast. Um, Dogs do a little bit better. Cheetahs do a little bit better. And we are way over here. So we were pretty happy about this. But unfortunately, there's this Southern California mite. I don't know if you get these in Mexico, but apparently they're very fast considering their size. And so we realized, though, that these creatures are going through air. Our droplet is going through water, which is like whatever, 100 times more viscous. So we said, okay, maybe we shouldn't compare that. We should compare it to other aquatic creatures. So the shark and fish, shrimp. Well, we're way, way better. So I think that this is the fastest, the fastest creature in liquid environment. I don't know if no one is. No, I've never heard of any great application of this, but it's just kind of for fun. Okay, so in this example, I showed you that gallium really likes other metals. And there was a question on Monday, and it caused me to go back and revise my slides because I wanted to show you one other thing. So if gallium likes other metals, and we thought, well, maybe we can use this to our advantage. So we mixed some gallium with copper powder, and we mixed them together in a mortar and pestle, just mix them together. And for a short period of time, they actually have a paste-like quality, but eventually they solidify. And this is, most of you are too young to know this, but if you have cavities, like when I was a kid, they would drill out the decayed part of your tooth and then fill it with what's called a dental amalgam. And instead of gallium and copper, they would use mercury and silver. And the idea is the dentist would mix them together just like this and stick it in your tooth, and then it would become solid. So we thought we could use this to make patterns. So we take this paste, it's kind of like toothpaste, and we spread it over a mold. We then heat it to about 60 degrees Celsius, and it will solidify, and we can take it off. And this allows us to pattern metals at room temperature. So this is all done at room temperature. And then in the end, you get something it's an alloy, copper gallium 2, and its melting point is 485 degrees Celsius. And so that's about 500 degrees, well, 450 degrees hotter than room temperature. So this is pretty cool because it's a way to pattern metals at low temperatures. Now, the problem with this, just to be honest, is these types of materials are called intermetallics, and they don't have great mechanical properties. So it is quite hard, but it's also brittle. Okay, so the last way to move metal around that I was hoping to talk about is by using surface tension. And this is kind of exciting work. On Monday, somebody asked about electrochemistry, I believe, and so I'm going to talk about that a little bit. So the general idea here is that we want to be able to control the shape of the metal, and because it's a liquid, there's ways that you could imagine doing that. And so there's this statement here: shape defines function. Well, that's kind of a little philosophical, but here's a very simple example. This thing is like a cane, and then this, obviously, when it opens up, it's an umbrella. It's the exact same materials, but you're just changing the shape. Okay, so how are we going to do this? Well, one way to do it is to use mechanical forces, and I showed you that on Monday, where you can take it and you can stretch it inside of an elastomer. Okay, another way you might do it, and as a chemical engineer, this is the way I would probably choose to do it, is to pump it. But the problem is that this is one of these microchannels, and the problem is that the liquid metal tends to stick to the microchannel walls. And so it's because of this oxide layer, it's very sticky to most surfaces, that you can't just pump it and move it back out. It's kind of like wet paint. So we would really like to do this electrically. because if you can do it electrically, you have better control over it anyway. So that's kind of exciting. All right, so how do you do this? Well, we actually do this using electrochemistry. So in this video, let me pause it for just 1 second. So what you're looking at is a puddle of the liquid metal, and it's sitting in salt water. And the idea is that right now it has an oxide layer on the surface, but it's very thin. And if we apply reducing potential, so we give it some electrons, we can convert the oxide, which is a solid, into gallium, which is a liquid. So here we go. We're going to take 2 electrodes and apply about -1 volt. And you'll see that we can remove the oxide layer and the metal will bead up due to surface tension. Now, I want to point out one thing at the very end of this video. If you look at the very end of the video, you'll see that when the metal beads up, it looks like smoke, like right over here, but that's actually hydrogen bubbles. So once you reduce the oxide layer, the metal can react with the water and it can form bubbles. Okay, so what is this good for? Well, just for fun, we made a maze, and I'm going to pause this also. We made a microfluidic channel maze. And there's an inlet, which is over here, and you can see that there's a droplet of water sitting on top of this. And then there's an outlet down here, which has a droplet of liquid metal. You can see that there's an electrode connected to the liquid metal, and there's an electrode, you can barely see it, but it's right here. So we're going to apply a voltage, and that voltage is going to remove the oxide from the liquid metal. And you'll see that this will solve the maze, because the solution to the maze is the electrical path. So what's happening here is that where this is withdrawing, like right here, the oxide is getting removed by this electrochemical reaction. Now, for this reaction to occur, there has to be water. And so basically, as this thing starts pulling out, it's like a piston, and it pulls this water into this channel. So there is an electrical path from this electrode over to this electrode via water that gets pulled into this path. Okay, so this is, I think that this is cool. Like, it's kind of exciting because you can solve a maze. But the physics are, in my opinion, sort of obvious, because once you remove the oxide layer, the metal simply wants to bead up. And so let me remind you of that. So this is the same video I showed you before. Remember that without the oxide, the metal just beads up. And so all we're doing is just removing it electrochemically. So, to go back to this video, naively, if you wanted to get the metal to go back in, what you might think is, oh, I'll just take the red and the black electrodes and I'll switch them. But the problem with that is, instead of removing the oxide, you would actually start depositing the oxide, and nothing should happen. So let me show you what does happen, which is very surprising. So again, all the experiments I'm going to show you are in sodium hydroxide, which is this electrolyte it's a base, and it removes the oxide layer. Okay, so here is a droplet of the metal. Again, this eutectic gallium indium, and it's sitting in sodium hydroxide. So there's no oxide layer, and because of that, you can see the droplet is very spherical. It's connected to a syringe, which is how we apply voltage, and we're going to apply voltage. Now, let me remind you, when we're going to apply 1 volt. And when we do that, all that should happen is you should deposit oxide on the surface, and nothing interesting. This should be the most boring video in the world, but let me show you. So we're going to apply a voltage, and something weird's happening. The metal starts to spread. It starts to form a pancake. And I might actually play this one more time just to make a couple points. So first of all, there's a lot of weird things here. Number one, liquid metals, remember, they have large surface tension and they want to form spheres. Somehow this is forming a pancake, very, very flat. Number two is there's electrical connection, this kind of stem of material that's connected from the syringe to the liquid metal. That's weird. You can even see there's some kind of looks like dirt or something on the surface. That's weird. And if I play it one more time, if you watch the contact angle here, it actually never is wetting. It never, maybe I can pause it. right here. Even though it's spreading out, it still has a very large contact angle. And that means it should not want to spread, but it still is. So there's a lot of weird things here, and I'm going to try to explain what's happening. But before I do, let me show you just one more video. So this video, you're looking from the top down. Let me start it over again. So what we have here is, what is that? 5 liquid metal droplets, and they're sitting in a mold. So you're looking top down. So gravity's pushing into the screen, and initially it is at high surface tension. So it's a sphere, and if you apply a voltage, which you can do because there's electrodes underneath it, it will squish down into the mold. And then when you switch the voltage off, it beads back up. Okay, so this is really weird. And one of the reasons it's really weird is that liquid metals have enormous surface tension. So if you think about like organics, like gasoline, for example, it's a typical surface tension value would be about 20 to 30 millinewtons per meter. Now, I know when I was an undergraduate, I didn't think about these units. So don't worry about these units. Just look at the numbers. 20, water, which is very polar, is 72. So that's considered huge. Gallium and other metals are like 500, 700, sometimes 1,000. So really, really large. And this is the largest one at room temperature. What that means is the metal should want to form a sphere. And so this is what it should look like. So here it is sitting in electrolyte. Now, when we first observed this, we thought that what we had was a classic phenomenon called electrocapillarity. This has been known since the late 1800s. And I'm going to try to explain it just very briefly. This is a plot of surface tension. So again, the larger the surface tension, the more spherical the droplet's going to be, versus potential. And if you wanted to try to get a liquid metal to behave like, to lower its surface tension, there's one way you can do it, is to apply a potential. And if you apply a positive potential to the metal, that should attract negative ions from solution, which are these red negative charge. And if you look at this, think about it, this should look like kind of like a typical circuit element, which is a capacitor. And so therefore, the equation that describes the shape of the surface tension is the surface tension is equal to the surface tension at the point of zero charge. That's the peak of this parabola, minus 1/2 CV squared. So this is if you remember from freshman physics, this is the equation for a capacitor. And it's describing the effect of this charge on the energy of that surface. So because the voltage is squared, it doesn't matter if you apply a positive voltage or a negative voltage. Either way, you get the same effect, and you should get a symmetric parabola. Now, I want to make a couple comments about this. Number one, if you look at this equation, you should get very excited, because what this means is if I apply a big enough voltage, I can make the surface tension be 0 or even negative. But you can see this is data from 1965. And in this data, they stopped measuring right here. And the reason they stopped measuring is because if you go too far of a voltage, you actually get electrolysis of water. In other words, these charges start combining and you start getting reactions. So there's a limited window of voltage that you can do this. Okay, that's one thing. Number two is if you look at the change in tension, in this case, it's going from about 600 down to 500. Now that is actually a pretty big change in tension. However, it's still at a very overall large tension. And the way I'd like to explain this is, imagine going from a 600-story building to a 500-story building. I know that doesn't exist, but imagine doing that. That change, that you don't want to take the stairs. That's going to be very tiring to go that distance. However, you also don't want to jump off the building, because 500 is still a very, very big number. So for a number of reasons, we don't think that this effect is electrocapillarity. So I'm kind of sorry, because I just explained something that actually does not explain what we're seeing. But I needed to explain this, because what I'm showing you is different than over 150 years of science and theory. Okay, so we think it's not electrocapillarity because in our case, when we apply negative voltage, the metal will beat up, and actually you can see hydrogen bubbles forming on the surface. And if we apply positive voltage, it starts to spread. Okay, so what do? Well, we go to the lab and we try to measure something. And the thing we try to measure is the actual surface tension. We call it interfacial tension because it's in contact with another liquid. But anyway, the way we do this is very simple. We look at the shape of a droplet, and it's called a sessile droplet. It's just a droplet resting on a surface. And there's two forces. We assume there's two forces: surface tension, which wants this to be a sphere, okay, and gravity, which wants it to be flat. And so depending on the shape, you can figure out the surface tension. So this shows you our experiment. We've got a metal wire, a very small metal wire that contacts the liquid metal. It's sitting on a surface, and we're doing this in sodium hydroxide, so there's no oxide layer, at least not initially. And when we apply the voltage, the droplet is going to squish down, and depending on that height, we can figure out the surface tension. All right, so here is our experiment. Again, you're looking at a droplet of the liquid metal. There's a little electrode that sticks up and touches it from the bottom. And there's a counter electrode, which you can't see. It's somewhere, I can't remember, somewhere over here. And what we're going to plot over here is the surface tension. So remember, water is 70. So water is right here. Gasoline is right here. So most fluids you encounter are way down here. And we're going to measure it as a function of voltage. Now, I need to mention one more thing that I find kind of annoying. And that is that with electrochemistry, these potentials are always measured relative to something. And so when you see negative 1.5 here, we're actually not applying anything. All we're doing is sticking these materials into the electrolyte. So everything is measured relative to this. So you can think of this as 0. All right, enough talking. Let me show you the results. So here we go. We're at this large surface tension. We apply a little bit of voltage. The tension goes down. It goes down more. We can go back, completely back and forth. So again, from the shape, we can get the surface tension, which is the y-axis. And by controlling the voltage, we can control the x-axis. So this is completely reversible. Now, if you remember the theory that I told you from the 1800s, it predicts that this shape should be a parabola. And actually, it is a parabola right here. You wouldn't know it from looking at it. It looks like a straight line, but it is a parabola. And something very weird happens right at this point. So we had to make some electrochemistry measurements. And I'm not going to go into a lot of detail, but basically we measure current while we apply the voltage. And you see right here, this is 0. So we start, remember, around negative 1.5, and we start applying a potential, and we see a little bump. And where you see that bump, that means there's a reaction occurring. There's electrochemistry happening. And so if you draw a dotted line down around this bump, around here, now I'm going to go over to this chart, and I'm going to put that same dotted line, and that's exactly where we see this weird behavior. So what I'm telling you is that to the left of this dotted line, this behaves like the theory from the 1800s. It's an old theory. It's not that surprising. But over here, we get surface oxidation. And for some reason, that lowers the surface tension. I'll be very honest, we don't fully understand this, and we could probably use your help. Let me tell you one of the things we're thinking is happening. So we think that the oxide acts like a surfactant. And you may not know this word, but I hope that you have experienced this word today, because a surfactant is something like soap. So if you have two dissimilar liquids, say oil and water, and you want them to mix together, you can add soap. And this is how we, wash our hair, wash our hands. It helps to remove the oil from our hands and our body. So as from experience, it's very easy to put the soap into the water, but it's very difficult to get it to come back out fact, it's nearly impossible without doing some, chemical processing. Well, in our case, with the liquid metal, we can apply 1 volt and we deposit the oxide layer. And so with the oxide, it acts like very low surface tension. And then when we remove it using -1 volt, remember it beads up and it's got this very, very large surface tension. This begs the question, why does it act like a surfactant? And at this point, we can only give you sort of our best guess. This is a diagram that shows how soap works. So again, with soap, you've got your oil that could be on your skin, and you've got water, which is coming out from your faucet. And this molecule that's in between them is a little bit confused. It's got this chain here that really likes oil, and it's got this ionic part that really likes water. And so it's sort of like holding hands between two enemies. It spans this interface and lowers the interfacial tension. If you were going to design a surfactant for liquid metal, you would want to have gallium at this interface with the liquid metal and OH groups at this interface with the water. If you look at this diagram, you realize right away that I'm not a chemist, and a chemist would never draw it this way. But what I'm trying to depict actually is the oxide layer. So the oxide layer consists of gallium, and then these red circles are oxygen. And so gallium, oxygen bonds that terminate at this surface with OH. So if you think, like, likes, like, I don't know if you've heard that saying in chemistry, but the water should be happy at this interface. And then the last thing that's bonded down here is gallium. And so this interface should also be quite happy. Now, to give you an appreciation for how big the changes that we're getting in tension, if you look at this plot of surface tension of water, remember water is about 72, so it's up here. And if you start adding soap, which is called SDS, sodium dodecyl sulfate, as you start adding in, this is a log scale, you'll see that the surface tension will drop, but at some point it doesn't drop anymore. And that's because the surface is completely covered with these surfactant molecules. Anyway, if you put that delta from 70 to 40 on our plot, it's this little point here. It's really cute. It's nice and little. That's what soap does. In our case, remember, we're going from 500 down to almost 0. Now, if you look at this plot, you should be kind of mad at me a little bit, or maybe mad at my student, because golly, why did they not measure one more data point? Doesn't that look like if it were to go down to here, it should be 0 surface tension? And isn't that interesting? I don't really know of any materials that have 0 surface tension. That's very, very strange, because if something has 0 surface tension, it should basically just mix. So the reason that we don't have a data point there is because the technique we're using doesn't work anymore. So let me show you what happens at that point. So this is some work we've been doing with Karen Daniels in physics at NC State. And what we do is we put a droplet of liquid metal in a little dish, a little petri dish, and we have a counter electrode, which is this ring that goes around the outside, and we contact the liquid metal again with a little electrode underneath it. Now, in the video I'm going to play for you, let me go back. I'm going to apply the voltage that looks like this should be 0 surface tension if you took this and projected it all the way down. And so we're going to look from the top down. And remember, if there's 0 surface tension, there's no energetic penalty for a material to spread. So let's see what happens. So here's the liquid metal. We apply that voltage, and the metal starts to spread. And it not only does it spread, but it actually starts forming fractals. Now, this is really weird, because we're only applying 1 volt, or a little bit less than 1 volt. Now, you'll see at some point that some of these little things will break, like that one breaks. Remember, the electrode is right here. So as soon as it breaks, it's not connected to the electrode anymore, and the oxide dissolves off and it just beads up. So clearly this is driven by this electric field. And then when you turn the voltage off, it just all beads up. So the implication here is we're lowering the surface tension very, very low. And to give you an appreciation for this, because again, I don't think most students think about surface tension, because it's something that's really only important at small length scales. So if you take that, this is a plot of surface tension for different materials. So over here you have water, which remember water is 70, about 72. And if you apply soap to it, it goes down to about 40. So that's, maybe a factor of 2 change. And over here we've got the liquid metal, which is between 5 to 700, depending on the environment it's in. And when we apply it at 1 volt, it's basically 0. So if these numbers don't mean something to you, let me actually, this is a slide I use with American audiences, so I'm sorry that I don't have any kilograms. But if you think about this in terms of pounds, you get rid of tension and you use pounds. So most people are about 150 pounds. Well, water would be like a dog, okay? And when you put the soap on the dog, it becomes a little bit of a smaller dog. So this is like 70 pounds. This is like 40 pounds. With the liquid metal, it's like a polar bear. So a polar bear is about 500 or 600 pounds. It's an enormous. And when we apply 1 volt, we turn it into a feather where it's basically 0. So recently we've been using this for a couple of fun things, and I'm excited to show you. So I've never shown this to anybody before. So one thing that we've done is to try to get little droplets of metal to jump. And to draw an analogy, so this is a classic physics experiment where you put a piece of metal or a weight on a spring. And as you leave it there to rest, it will come to some equilibrium position. Now, you have to use your imagination here, but imagine if you could take the spring constant and make it much smaller. If you made the spring constant smaller, the weight will then squish down to a new equilibrium height. If you could then suddenly return it back to K1, where it's a larger spring constant, it should then push the spring and cause it to jump. Well, in our case, it's not easy to change a spring constant, but in our case, we go from a droplet that's at about 500 millinewtons per meter at 0 volts. We apply a voltage and we make the tension about 0, so that causes it to squish. We then can very quickly apply a negative voltage and remove the oxide layer and cause it to go back to 500. So that's like making the spring constant high. And then when we do, it's got this excess energy. So it's spread out at a large area, but it's got a really large tension. So now it's going to come back together and jump. So let me show you the results. If you look, you can see this droplet jumping. So there's an electrode. It oxidizes the metal. So the metal spreads, and then we switch it really quickly. And that releases that energy and it will jump. So it's like a little toy. I don't know what this particular thing is good for, but there's a lot of people who've studied jumping droplets for improving heat transfer and other applications. But heat transfer is probably the most relevant. The idea being that you take heat from one surface and then you cause a droplet to jump and carry that heat away to another surface. Okay. So I think this is the last thing I was hoping to show you. And to motivate this is just another application of this interesting phenomenon. If you turn on your faucet, you will see, of course, water coming out. And if you have a little, very slow flow rate, you will get what's called dripping. And I didn't make this up, but this is what people in fluid dynamics call this. It's literally called dripping. Now, you could try to make something other than droplets by increasing the flow rate, but the stream will still break up, and it's called a Rayleigh plateau instability. So that same nozzle, if you increase the velocity, you can see that it will form a stream, and that stream, if you give it enough time, will break up into droplets because that minimizes the surface energy. So this is also driven by surface tension. So the time that is required for the stream to break up is proportional to the diameter, so it's labeled here D, to the third power. So what this means is if you make something really small, it's going to break up really fast. Another thing that matters is the surface tension. So the bigger the surface tension, which is squeezing like this, the faster it's going to break up. In other words, the shorter the time scale. And so with liquid metal, because we're going to make a really small stream, actually about 100 microns, that's about the size of a human hair. And remember, it's got this enormous surface tension. So when we pump the liquid metal out, you're going to see it's going to form droplets. However, as we start applying a voltage, you'll see that the droplets get smaller because the tension is going down, and smaller and smaller, until eventually at that magic voltage, about 0.8 volts, it comes out as a wire. And then if we apply too big of a voltage, we get a really thick oxide layer, and it actually starts behaving like candle wax, which is interesting, but we haven't really studied that. We've really studied just the formation of that wire. So this overcomes what's called Rayleigh plateau instabilities, which again is described by this picture. And again, there's a huge literature of people who've studied this since the 1800s, and every paper has the same conclusion. Liquid streams break up due to surface tension. I'm going to show you a video, and let's see if this will cooperate. If I can pause that, play this one. Okay, so in this, what you're seeing here is, it's really hard to see, but there's a little wire here. This is our liquid metal wire, and it's inside of a container. And here's our counter electrode, and we're pumping the liquid metal, and we're letting it fall by gravity. This is about the size of a human hair. So let's see if I can play this. So here it goes, and you'll see that it's stable all the way down this container, which is not quite a meter tall, but close to a meter. And just keeps going and going, and it's stable all the way down. And then at the very end, it collects. You can see there's a collection of liquid metal at the bottom. So this is really, really surprising, because if you look at this equation again, this is the size of a human hair, which means it's really small. It's the liquid with the largest surface tension known to man. So the denominator is also really big, and the density is also really big. So everything, everything in here sort of is working against you. So this video is just kind of for fun, but we made a little stair steps, and we dragged the liquid metal. And so you can see that I don't know why it's playing a little bit funny, but you can see that the liquid metal keeps its shape as it flows over these surfaces. So our studies of this, basically what we've shown is that the surface tension is, I think it's basically zero for all intents and purposes. But there's also a very thin, we think it's kind of like a molecular layer thick of oxide, and that also helps to stabilize these things because of the shell that's forming. We've used these same principles to control the size of droplets in microchannels. So I showed this earlier where we pumping liquid metal. So this is what our microfluidic device looks like. We pump liquid metal as well as another solution, and we squeeze everything through this little orifice. So you can see right here, that orifice. Here's another picture of it. Just the liquid metal getting pushed through here, and then this other stream, it all converges into that orifice. Well, this is great. And we've done this. And one way to change the size of these droplets is by changing the flow rates. But I can tell you from experience, whenever you change the flow rate, it takes about 10 minutes for it to come to some new steady state, because all the pressures and stuff get out of whack. Well, in this case, what we do is use voltage instead to control the surface tension. So when we apply 10 volts to the metal, we lower the tension, and we can form smaller droplets. And then 0 volts, it goes back to high surface tension, and it forms bigger droplets. And so you can do this in real time. This is actually a high-speed camera, so these things are coming out very, very fast. And so you can control the size of the droplets. And I showed this picture earlier, but just give you kind of an example. You can make these really beautiful microspheres of the metal. You can also use this principle to steer liquid metal. So let me pause this and explain what you're seeing here. This is liquid metal being pumped into a microchannel. And at the end of this channel, it has a decision to make. Do I go left or do I go right? And we're going to take a copper wire and put it into the outlet. And when we put it here, it makes the surface tension over here lower, which means it's easier for it to go to the right. So you'll see, let me start over. So you see it's going both ways. We then apply the voltage on the right, get it to go to the right, and then we switch to the left, and we can steer it in different directions. again, all of this is using this electrochemistry that's changing the surface tension of the metal. So this next one, this is my last slide, and the next one I meant to be funny, but I don't know if you're going to know this comedian. He used to be on Saturday Night Live, and he also is now a late night TV host. So maybe you know Seth Meyers.
This is really cool. This week, scientists at North Carolina State University announced they discovered a way to move and manipulate liquid metal with electricity. And Arnold Schwarzenegger has already been sent back in time to stop it.
So anyway, this was like a this was like a really a high for me to get mentioned on late night television and be made fun of by these comedians. So I always joke too that this is how we ended up stopping our research on liquid metals. So the summary from today, hopefully I've shown you that these, I'm calling them colloids, but they're just nanoparticles basically, are very easy to make, and they have some interesting uses, including moving them around. And then I also showed you how to change the shape of the liquid metal by using electrochemical reactions to decrease or increase the surface tension. It's completely reversible. Like last time, I really owe a huge deal of thanks to the amazing students that are in the group. They did the work, they get all the credit. I'm just the one that's lucky to be here to share it with you. And I also love collaborating with people. So I tried to mention people's names as I went, but these are some of the people I've been really lucky to work with, in the recent years. So there's a lot of different places that have supported this work, and I'm grateful for that support to enable this to happen. And then I think I showed this last time, but just to kind of leave this up in case anybody wants to jot down other places you can go to get information. So I think I finished about on time, and be very happy to answer questions like last time.
Thanks, Michael. Very interesting and amazing research you are doing. There are a lot of questions here.
Great.
The first one is from Alberto Beltran. So I will give him the chance. Yes.
Which one is that? Yeah, I was wondering for the experiments related to killing bacteria.
Yep.
You said that interestingly, the bigger the magnet, the larger the area of where bacteria are killed. So I wonder if there is motion in that area. Have you observed any motions that could be related to velocity gradients?
Yeah, so that's a good question. So basically what we think is happening is that the magnet is actually spinning.
Yes.
And depending on the size of the magnet and the path that it spins, that dictates, if you look at the slide, let's see, where's the size that you're seeing here is exactly where the magnetic field's getting spun. Now, that doesn't really answer why this is working. And in the original paper that, again, I want to be very clear, like I didn't do very much. I was lucky to be involved with this, but I didn't do very much. The people that did this work, they thought that what's happening is that the particles were spinning and becoming rods. I personally think that they may have already been rods, or maybe they become rods just because they get a little bit warm. But because of the iron, they can still spin. And so they sort of get stuck to the bacteria, and then they're getting pulled by the magnetic field. But what we really need to do is some additional control experiments, because if that's the case, you would think, well, maybe just like iron rods, maybe like iron rod would work. Why do you even need the gallium? And I think that the gallium, because it also has antibacterial properties, I think that that's probably helping. But unfortunately, we haven't done that control experiment. So yeah. Oh, I think you're muted. I'm sorry, I'm not hearing what you're saying.
No, yeah, you answered my question. Thank you very much.
Oh, okay. Thank you.
Bye.
Thanks a lot. Good to see you.
Good to see you too.
Okay, there is one more question. Is in some more, but one that is related to this question that just stated Alberto, and he is asking about some different ways to control the liquid metal using high or low frequencies. But I will add how the frequencies that you are using, for example, in this experiment and in some others.
Yeah. So, I mean, frequency, I'm not sure. There's a lot of different ways to interpret that, but like, I mean, in this case, the frequency here is based on the frequency of the rotational motion of the magnet. And this is just, this is kind of like a magnet that you would use for like a stir plate. So I don't remember what the RPMs are, but it is a good question. And I don't know that we've really controlled for it very carefully. I'm sort of wondering if maybe the question might have more to do with like RF frequencies. And in terms of the particles themselves, I thought I had a really good idea a few years ago, which was to take the particles and use microwaves to heat them up, because you're never supposed to put metals in a microwave because they spark and whatever. But what I found was, and I don't understand this why it doesn't work, but I think because the particles are so small, it doesn't really work. So the stuff that we've done in the RF, and I'm sort of guessing here, and please feel free to clarify your question, but in the RF, we've made antennas, and I think I may have shown some of those on Monday, but they're more like, centimeter length scale, and they actually can resonate. And in that case, I guess that's sort of a way to control them. I mean, you're not really changing much about them, but you can actually use them as antennas. You might also be referring to the frequency of the motion of, physically moving them back and forth. That's a really good question. And in that case, I don't really have a good answer, because it would depend on the way that you do it. A lot of these things we're doing in liquid environments, which means they're kind of dissipative because you're having to move liquid around. But I'm just trying to imagine, like, suppose you wanted to move liquid metal particle really, really fast, like really, really fast back and forth. I'm not sure the best way to do it.
Okay, it's a difficult question because you have a two-phase flow in this case, and it depends on the dynamics, and yes.
Yeah, I like the question. I would need to think about that. I'm not sure.
Okay, maybe it's related to the previous one. Arnoldo, please, you can turn on your microphone.
Yes. Can you hear me?
Yes.
Oh. First of all, thank you so much for your presentation. It was incredible and inspirational for students of first grade like me and my classmates, obviously. And
thank
my
you
question is,
thank you.
Well, my question is, can the Navier-Stokes equations predict the movement of liquid metals, especially when they flow?
Well, yeah, that's another good question. So the answer is that I think it should. The only thing that gives the liquid metal sort of unusual rheological behavior is the fact you have this oxide layer, right? So if you don't have the oxide layer, and you're just talking about liquid metal flowing through a pipe or something like that, it's literally its viscosity is 2 times that of water. And so it should just act like a Newtonian fluid and kind of in some ways be sort of boring. When you have the oxide layer, it in some ways it acts like surface tension in the sense that it resists flow. And so off the top of my head, I don't know how you would build that into the equations, but basically above some critical pressure or stress, it will start flowing basically like a viscous liquid. So yeah, I'm trying to be a little bit careful in my answer because I don't know for sure because I've never tried it. But my feeling is that as long as you accounted for its rheological behavior, I don't see why those equations wouldn't apply.
Okay. Well, thank you.
Yeah, sure.
Thanks, Arnoldo. Carla?
Hello.
Hi, Carla.
I have a lot of questions. It's about the experiment when you put the droplets and you make the pattern of fractals. I think this could be a short-cut current because then it will break. So it seems like when you burn wood with a lot of current, so it looks like you have a short current.
Are you? So I heard only part of the question. Are you referring to the work where we squish the particles, where we push on them?
Yes, when you see the fractal pattern.
Is it this work here?
No.
About the fractals that you showed us.
I'm sorry. Yeah, sorry, the audio wasn't very great on my side. Let's see. Oh, wow, I jumped right to it. This one, right?
Yes. When it breaks, it seems like you having a short current because, well, it forms that pattern, and it looks like when you burn wood with a lot of current. You can see any of that video?
Yes. So maybe let me show this previous slide. So what we're doing is we've got a droplet, and I don't remember the exact diameter, but it's maybe 2 or 3 millimeters, maybe. And it is sitting on a very flat surface. So we have to have this surface to be flat because if not, the droplet will roll off one way or roll off the other. And then we contact it with a wire, copper wire from the bottom, and we use the rest of the circuit is there's sodium hydroxide solution, and then there's a counter electrode that goes all the way around that, so the current is going radially outwards. Although it turns out that doesn't really matter. But we did this to make it symmetric.
But you can measure the current?
Yep, we've measured it, and we're still studying this. So I go back. It's actually more complicated than I explained. So this is actually where we measure the current. And so if you look, it's first of all, it's a little hard to see, but this is 0 current. So we actually start right around here. And we start applying a positive voltage. So we move to the right, and you see there's a little bump. That's actually where the oxide first deposits. But when that happens, the surface tension doesn't change very much. It changes just a little bit. And then we keep applying a voltage. And then at some point you see that it goes way up. And where we see it around 0 surface tension is right around here. So the point is that the oxide actually initially deposits, but it's not until higher potentials that we start to see it really start to form those instabilities. But you'll notice that when the oxide does first form, the tension drops, and then it drops some more, and it drops some more, and it drops some more. And Frank, we don't know why. I think that it could have to do with charge on the surface, depending on what the chemical species are that are forming. And it could also be due to driving charge through the oxide layer. So if you imagine you have an oxide layer and you drive like a charge through it, that pushes the oxide outwards and generates a stress. So
question is, if you that kind of experiment, you can also put a magnetic field, maybe of a magnet, of electromagnet.
Yes. Actually, yeah, I'm smiling because it's a great idea. It actually works, and it's really interesting.
And if that could control better the wearability abilities of the droplets.
Well, so yeah, so we have some collaborative work, and I can, well, so where we have the fibers coming down, there's a couple more slides. Let's see. This one, where let me pause that. So this one, where we have this really long wire, if you take a magnet and put it behind it, it will actually cause the wire to move because you have a Lorentz force. So basically you have current going through the wire like this, and you have a magnetic field behind it. And, it's like the cross product. You've got current in one way, magnetic field in the other, and that generates a force in the third dimension. So that it's a brilliant idea, and it definitely works. I don't have it here in my presentation because it was actually with some collaborators, and I didn't know if they were okay with me showing it. But yeah, it works. It's a great idea.
And finally, have you studied the hydraulic instability mathematically? I don't know, taking account the stability analysis with the electric field applied, because it's also interesting because you can overcome that instability.
Yeah, so well, I guess the answer is yes and no. So I'm not completely satisfied with how much we've studied it. I think there's still some more questions that I'd like to answer. But one of the challenges, if you look at this video, for example, it actually never becomes unstable. So, in terms of studying an instability, if it doesn't happen, it makes it very difficult to study. Now, I think what your question is, why? Like, why is it stable? And at this point, I can sort of only offer two explanations. One is that the surface tension is just very, very low at that point, and it could even be 0 or negative, which is kind of weird to think about, but so that's one thing that works in our favor. But we did a couple of other things, and although it's not very scientific, like this video is just one example where we like draped the wire over different surfaces and we pulled on it. And if you have a liquid that is draped like this and it's purely viscous, gravity should pull it down like this. Well, what we found is if we pulled on one side, we could actually pick the whole thing up, which tells me that there's something solid-like on the surface that's like a shell. And so this was the one thing in our paper that we published that we were never able to distinguish, because we have low tension, which is important, but we also have this solid-like shell that's probably helping to stabilize it.
But you apply the voltage, no? Because it is possible to take in account the electric force.
Yes.
that
Yeah.
overcome the instability?
Well, so the voltage that we're applying is like less than 1 volt. So there's no significant electrostatic forces according to our calculations. So this is really driven by electrochemistry. And so if you look at the Rayleigh equations, like, I mean, just the most simplest one, it would be like this one, for example. This tells you how fast the stream should break up. And so, you know, if you know the density, which we do, you know the diameter, which we do, maybe you could say, well, we don't really know the surface tension, but if we wanted to measure the surface tension, we would need to know the time for it to break up. This is directly from the Rayleigh. This is a scaling law from Rayleigh instability analysis. And that time scale it never breaks up. So what we did is we said, well, okay, if in this container, this blue container, it takes 18 seconds for the liquid to flow from the top to the bottom. And so if you plug in 18 seconds here and all the other numbers here, you get a surface tension is like 10 to the minus 7 or something. I can't remember. It was like a really low number. And so at some point we basically just said, well, effectively the surface tension's got to be like 0. But then and I'm sorry, I'm probably saying way more than you had intended to ask, but the question is this equation even valid? Because if you actually have a solid oxide on the surface, then is it really free to flow? Like, maybe not. But if you look really carefully at this video, you'll notice something kind of interesting. So if you watch right here, you'll see that the metal, it actually, oh, shoot. Sorry. I'm trying to pause it. For some reason I'm not able to pause it. Let me see if I do this. If you look at this region here, when we lay this wire down, and I wish I have other videos I would love to show you, but when we lay that wire down, it actually continues to spread. In other words, if it has the ability, it will continue to increase its area. So the cylinder doesn't even maximize the area. It will continue to increase its area by trying to spread on this flat surface. So I wish I had like a more satisfying answer, because I mean, I probably could have just said we don't really know, but I thought I'd at least tell you that we're trying to understand it.
Okay. Thanks, Carla, for the questions. Montserrat, you have another question?
Yeah, in the diagram, tension superficial that you showed.
Oh, the diagram of what?
The
Surface
superficial tension and voltage.
This one, right?
Before. Yeah.
Or?
The one before. One more, please.
Or keep going?
Yeah, you say that water and organic should be like in the corner, like very low.
Yeah.
Like in the 0 and minus 2.5. So what that very leaves the other liquid metals like mercury.
Yeah, so that's an interesting thing. So we've only done like one experiment with mercury because my students were scared, and that's fine. Like, I don't want them to be scared of using materials. So we tried this with mercury, and mercury does oxidize, So if you see the experiments, mercury starts out very shiny, just like the Terminator. And then when you apply an oxidizing potential, the surface gets kind of black and nothing happens. So there's something about the gallium oxide that's special. And I don't know if it's because it forms a passivating oxide, like where it completely covers the surface, or if it's because of the way it charges or something, we don't know. The biggest challenge we've had with this project, and the reason I'm not able to give very good answers, is that as soon as you turn the voltage off, whatever is on the surface just dissolves into the electrolyte. And so what we would really love is to know what's actually on the surface, because that's kind of the key for this phenomenon. So I guess to answer your question, like mercury behaves like this left-hand side, but mercury doesn't drop in tension, at least in our experience. We only tried it one time, but we didn't see a big drop.
There is one more question in YouTube. It's Amali asks if there are some other morphologies that you have found in the liquid metals nanoparticles.
Yeah, so the only two morphologies that I showed today were a sphere and a rod, but the rod was actually a crystal. It's not even liquid metal. Other groups have done really beautiful work where they've somehow sheared the metal and made it into an ellipse, like a more or like less round but more rod-like. And actually, I saw just yesterday, I saw a paper where people had taken the liquid metal and put it into some pores, into a filter, and then they dissolved away the filter, and they were actually able to make nanorods out of liquid metal, which I'm still very surprised that works. But it suggests that, you know, depending on how you make it, if you have the oxide layer, that you could actually stabilize the metal. But the approaches that I've shown here, like sonication and stuff, those tend to be spheres. Now, some people have done some work where they've taken liquid metal and they mixed it with silicone, some like a really viscous liquid. And in that case, you can get, like, I call them blobs, but they're just non-spherical kind of random shapes. What's difficult to do is to make sharp corners because of the surface tension. It doesn't like to be like this. It prefers to be rounded. So that's, and then of course, the smaller you get, the bigger the interfacial forces become. And so that's another challenge.
Thanks. Gabriela Cortez, you can promote yourself, Gabriela.
Can you hear me correctly?
Yes.
Yeah, thank you.
My question is, what technologies we use daily use liquid metals? I refer, any of these experiments are already introduced into the industry, like our cell phones, computers, or something like that, or are still experiments?
Yeah, that's a good question. I'm sorry I didn't touch on that in the talk, because I know that's definitely of interest to people. Yeah, as far as I know, gallium is not used. Everything I showed, none of that is used in industry. What I've generally found is that there's, whenever people hear about liquid metals, they either think it's toxic or there's some other issue that they somehow have in their mind. So I think part of it is just trying to convince people that it's okay. But people have used it for, not as a liquid metal, but have used it as a material in like semiconductors, for example. So it's used in gallium arsenide and gallium nitride. These are materials that have really great semiconducting properties. And then there's also, right now, there's a lot of interest in gallium oxide for what's called power electronics. So electronics that operate at really large voltages. And this is important for, like, you know, if we go to a green economy or a green power grid where you use solar energy or batteries and these kinds of things that you need electronics that can operate at really high potentials. And so there's actually in Raleigh where we live, there's the United States has a research center called Power America, and one of their focuses is on gallium oxide as a material for those types of things. So it's not like it doesn't have applications. It's just the way that I've presented it here, we're really taking advantage of the liquid properties, and those properties, as far as I know, have not really been used.
Mm.
Yeah.
Okay, thanks.
Yeah, thank you.
Just a couple of questions more. Lisette is asking about the disadvantages of using these nanoparticles that you mentioned. I guess that she refers to the maybe health issues or something like that.
Got it. Well, I guess it really depends what you're trying to do with them. One of the couple of the challenges that we have faced, and I can only speak for us, and but one of the things is that if you don't make them properly, like they're not small enough, or you don't treat them the right way, they can settle over time. So they will settle in the vial because they're dense, and so that's one thing. And I think we've pretty much solved that issue. We've created pretty stable suspensions, and other people have too. The other thing that's been a little bit problematic is that if you make these things in water, they will react and form that gallium oxide, which I mentioned. So we've created a coating, which I didn't show, but we've created a coating that helps stabilize those particles for weeks at a time. And then there's been some work from some other groups that have also put polymers on the surface of the metal to help stabilize it. So those are the two things that kind of come to mind. The other thing was that at least for me, like when we first started working on this, I really thought that this would be exciting because we could make conductors. And it turns out that it's actually quite difficult to make the particles into a conductor, because once they're really small, it's not so easy to merge them together. So that's kind of another thing. And there's a really beautiful paper that came out in the past year where they use chemical reactions to stick the particles together. And then when you pull on them, they break and merge together. So that's like a way of taking the little particles and getting them to all stick together. Yeah, those are the three that come to mind in terms of challenges that still exist a little bit.
Okay. David Padilla has another question.
Yes, hi. Well, first of all, thanks for your presentation.
Thank you.
That was amazing. Well, my question is, have you ever tried using an alternating voltage or current? What I mean, there is an experiment in which you have a thread of water in which you use sand to make different shapes of the thread of water. So is it possible to make something with the liquid metal, like changing the current to the voltage?
Yeah, that's a great question, and it doesn't have a really easy answer. So the short answer is we've tried it a little bit, and the thinking is that if you imagine an AC voltage, so say that this is 0. Well, when you go to positive, you oxidize the metal as long as you get a high enough voltage, and then when you go to the negative part, you could reduce it. Now I'm talking about an electrolyte. If you don't have it in electrolyte, it's probably not very interesting. And so we've done a little bit of that because the thinking was that it would sort of help control the shape. And I would say that we were never really able to control it very well. And so it didn't work as well as I hoped. But that's not to say that it's not worth exploring again. The other thing that comes to mind that does work is if you put a droplet of the liquid metal in a tube. Actually, let me see if I can draw it on here. So imagine you have a tube like this. Hopefully you can see the drawing. And if you have the liquid metal in the tube like this, then you can apply AC voltage like this to both sides, and you can actually get the metal to move back and forth. And this is called continuous electrowetting. Continuous electrowetting, and we're actually working on that. We've worked on it and we're working on it right now. The basic idea is that when you apply, let's just say positive voltage here and negative voltage here, then let's see, I have to remember that's positive. I think that becomes negative at this surface, and this becomes positive at this surface. And so as a result, you get a gradient in surface tension that causes the metal to move back and forth. And that works very well. That is a good way to move the metal. Actually, I probably should have shown that because this is pretty simple and pretty easy to do. And one of the reasons it works is that the electrolyte, so everything else that you see in here, this is all water. Water, there's actually a little thin layer that seems to form between the liquid metal and the walls, and that makes it so it doesn't stick. So it allows it to slip. So anyway, so that's one thing that people have done with AC that comes to mind. Yeah. These are great questions. Thank you.
Okay, we end up with a question that has Mariana.
Hi.
Hi.
Thank you for your presentation. And I have a question. Have you done experiments about biocompatibility in human body or only for bacteria?
Yeah, that's a great question. Yeah, we actually have. Well, let's see. So yeah, I don't know that I have a slide handy to show you, but we've done a few things. So first of all, a while ago, we did some experiments where we took liquid droplets and we were using them to try to kill cancer cells. And so in that work, and again, this was collaborative. So when I say we, I mean all the people that worked on it. We put the little particles into mice, and the mice were able to clear it from their body. So they remove it through their kidneys primarily. So there's that. We also did something where we took liquid metal and we contacted it to neurons, like from your brain. And neurons are famous for being very, very sensitive to their surroundings. So if there's like any disturbance, they typically die. And in our case, we found that they were very healthy. So they formed axons and there was no problem. In terms of like the human body, there's been some studies that show that gallium, and when I say gallium, I really mean gallium 3+. So, you know, if you take a vitamin, like let's say you take iron, like an iron supplement, like a vitamin that you eat, it's not metallic iron, it's like iron 3+ or iron 2+, it's some kind of salt. And so when I say these things in the body, it's really the salts. So like magnesium in your body or calcium in your body or iron, they're all salts. They're not in the metallic state. So people have studied this and shown that gallium is safe, even though it's kind of strange. It's not found in the body. And part of the reason it's safe is because it actually has the same charge and the same radius approximately as iron. And so again, if you take a vitamin and you have iron, your body removes it through a certain mechanism, and gallium is the same way. So kind of the final thing is, well, what about the metal? Like what if the metal gets in your body? And I think the answer is I don't really know, but I had a collaboration with some people that were interested in using this, and they actually took a needle and then injected it into the skin of a rabbit, which I would not want to do personally. But I told them, it's kind of a funny story. I told them that's like, oh, I would really like to see the results when you get the results. And they said, okay, yeah, sure. Well, then maybe 1 month later, I got a package in the mail and I opened it, and it was this plastic package with this like pink stuff inside. And I was like, what is this? And I contacted the people and I said, I got this package. I don't know what it is. And they said, oh, that's the rabbit. And I was like, oh God. So they actually shipped, instead of sending me the results, they actually shipped me a cut of the rabbit skin. And so anyway, so these people, they worked at a hospital in Indiana, and they found that even if you inject it into the body, there was no issues. So I'm always trying to be careful when I talk about this, because I think it needs to be studied a little bit more, but I have yet to see anything that suggests it's dangerous.
Do not try at home, please.
Yeah, exactly. Exactly.
Okay, many thanks for your talk and all these questions. It's
Thank you
very
so much.
difficult multidisciplinary equipment that you require. Fluid
Yeah.
dynamics, electrics, and engineers, and so on and so forth. So we appreciate very much your presentation, and we thank you again for
Thank you.
being here today. And we hope, and we wait for the last presentation on Friday.
Yeah, it should be a lot of fun. And thank you everyone for your attention. I am just so impressed with the questions and the engagement. So thank you for your time and for paying attention and asking great questions. And I don't know that I answered them very well. So if you have some follow-up questions, please let me know, and I'd be happy to discuss some more.
Okay, thanks.
Right.
Okay, see you, Michael.
Okay, bye. I'm going to
Bye.
stop sharing.
Ok, bueno, en unos 15 minutos más o menos, tal vez un poco menos, empezamos la plática, el segundo curso de la doctora Sandra Rodil. Vamos a terminar la sesión en YouTube. Muchas gracias, y en unos segundos volveremos a iniciar la sesión. Si tienen preguntas, por favor las pueden escribir aquí, y se las haremos llegar a Michael Dickey, quien respondió las preguntas también. Lo pueden revisar ahí en Moodle. Nos vemos en unos